Let's move on to look at the design of the decoder. That's another building block that's a standard component of computer devices. In fact, it's a component of random access memory chips, RAM. Like many jargon words, decoder means something different in this specialist application from what you might normally understand it to mean. In ordinary circumstances, we might think of a decoder as a person or a machine that converts information written in a secret code into plain English or French or Urdu or whatever language our own particular secret service speaks. Well, in a sense, our sort of decoder is doing something like that. It converts a number, represented using the standard voltages used in digital logic, and expressed using the binary number convention, which, although not secret, is a genuine code. It converts a number expressed this way into a high voltage on one wire out of a set of wires. So if the binary number is a 2-bit number that can have 4 possible values, then the decoder's output is a high voltage on one of 4 wires. Generally, each of those wires carries a control signal that activates some other circuit. So the overall arrangement would be that a binary number encoded onto a pair of wires would be input into the decoder, which would put a true output on one of its 4 output wires, and that would then be used to activate one of 4 other circuits. That would be a 2 to 4 decoder, like this one, which is a bit small for many applications, although it's certainly a useful device. But in computer memories, for example, the decoders are a whole lot bigger. Decoders that convert a 10-bit binary number to a true signal on one of 1024 outputs, or even 16 to 65,536. Decoders are not uncommon. We choose the small device for the practical reasons that the number of modules in a 4-bit device is enough to make the generalizations to larger devices self-evident, and because it's small enough so that we can draw the design on a single page. A lot of the circuits that we look at in this course will be 4-module devices for that very same reason. They're big enough for the generalization to larger sizes to be self-evident, and they're small enough to handle. So, let's move on to the actual design. There are 2 inputs which we'll call I0 and I1. Those are the bits of a binary number. I0 is the less significant bit, and I1 is the more significant bit of this number. If the input number is a 0, that is, if both bits of the number are 0, then the output wire, A, will have a true signal on it. If the input number is a 1, which means that the 1's bit is a 1 and the 2's bit is a 0, then output B will have a true signal on it. If the input value is 2, then output C will be true. And finally, if the input value is 3, our circuit is required to set output D to true. Our truth table will therefore have 2 columns of input, and our circuit diagram will have 2 input signals running down the left-hand side. There are 4 independent outputs, so there are 4 output columns on the truth table and 4 output wires driven by the circuit. We start, as usual, by listing all the input combinations, and then we show the outputs that are generated for each of those input combinations. This particular table has a very regular structure. Output A is true when the input binary number is 0. Output B is true when the input binary number is 1. Output C when we're inputting a 2, and output D when we're inputting a 3. So we end up with all those diagonal 1s in the table. Under all other circumstances, each of the outputs is false. So then we can write Boolean expressions for the outputs. There are 4, because there are 4 outputs. A is true when I0 and I1 are both 0, and under no other circumstances, so its Boolean expression is just a single term, not I1 and not I0. Note that the horizontal bars that represent the not operator apply to the individual factors in the term, not to the term as a whole, so don't draw them as a single horizontal bar across the whole thing, because that means something different, and in fact you can prove that it's different from this representation using a truth table if you want to. Each of the other outputs is also only true for a single input combination, so each of the other outputs also involves only one term. and you'll see that there's a close correspondence between the zeros in the input columns of the truth table and the locations of the horizontal bars that represent the not operators in the Boolean expression. Wherever there's a 0 in the input, there's a not operator in the corresponding expression. Now it's just a case of adding the AND gates to the circuit diagram. Output A is a single term, so it involves only a single AND gate that detects when both I1 and I0 are 0. So it gets connected up to wires carrying the inverse of I1 and the inverse of I0. Each of the other outputs is also generated by a single AND gate. This is output B, which is not I1 and I0. You should be able to see how easy it is to read the meaning of the connections off the diagram when each input and its inverse is shown on the left-hand side of the diagram, and the blobs of solder make it clear where the connections are. Remember that an AND gate will produce a true signal when all of its inputs are high. When I1 is a 0, there'll be a high voltage on the rightmost of the wires driven by I1. And when I0 is a 1, there'll be a high voltage on the leftmost of the two wires under the control of I0. So, just by looking at the position of those blobs of solder, it's possible to read off the expression that's implemented for B, not I1 and I0. Similarly, output C is driven by an AND gate that detects when I1 is 1 and I0 is 0. And D is true when I1 and I0 are both 1s. The simple decoder that we've just seen illustrates the basic decoding behavior well enough, but it isn't a realistic circuit component because although a simple decoder circuit can be used to activate one device out of a set, it can't be used to deactivate the whole set. That's because one of its outputs is always true. So one of the sets of devices that it controls will always be selected. Now, decoders are a standard component of memory chips. They convert a binary number that represents an address into an activation signal for a particular word in the memory. Well, the address wires always have some value on them, even if nothing's driving them. So, to prevent the memory from being activated at the wrong time and reading from or writing to arbitrary locations, we redesign the decoder so that we can explicitly force all of its outputs to be 0, irrespective of the value on the data input. That way we can ensure that the controlled devices will not be activated unless we want them to be. I've called the resulting device a more sophisticated decoder, and the only difference between it and the simple decoder is that we've added a single-bit control signal called output enable. Now, that in itself isn't a major complicating factor, but it does introduce a new concept. Control signals are often active low. That is, they take effect when their voltage is low. This particular control signal is an output enable control signal. It allows the decoder to have a true signal on one of its output wires when its voltage is low. When its voltage is high, none of the outputs can be true. Graphically, we indicate that the signal is active low by putting a little circle on the end of the wire and putting a horizontal bar over the name. So this control input enables the output when its voltage is low. That's probably the opposite of what you'd imagine might happen, but it's quite a common convention with control signals. Data signals mostly use a high voltage to mean true or 1 and a low voltage to mean false or 0. There are exceptions to that, though, as we'll see a few slides from now. So let's recap. The more sophisticated decoder behaves exactly the same as the simple decoder when the output enable input is low. One of its data outputs will be true, depending upon the value of the data input. When the output enable control signal is high, on the other hand, all of the outputs are false, irrespective of the values of the data inputs. So we can now start to draw the truth table. We do this in sections to demonstrate that the top part of the truth table is exactly the same as the truth table for the simple decoder. This corresponds to the situation where the output enable signal is low. Where the output enable voltage is high, then for all combinations of the data inputs, the output of the device is false, both along the diagonal and in the off-diagonal positions. The Boolean expressions for the outputs are simple. They are in fact identical to the Boolean expressions for the outputs of the simple decoder, except that each term now incorporates a not OE factor to indicate that the output cannot be true unless the output enabled voltage is low. Now we can start drawing up the circuit diagram. Again, it's very similar to the circuit diagram for the simple decoder. In fact, the data inputs are connected up to the AND gates in exactly the same configuration. However, we now have a third input, which is not yet shown on the diagram, so of course we need to use 3 input AND gates. And those gates need to detect when the output enable signal is low, so since AND gates usually detect high voltages, they are connected to the inverted OE signal, which will be high when OE is low. As we've already mentioned, decoders are used when you need to be able to activate one out of a set of devices at a time. A particular and important example of that occurs in RAM, random access memory, when you want to activate one word in memory to read information from it or write information to it. You supply an address to the memory, but that address is encoded as a binary number. It really needs to be a true signal on one of a large number of wires going to the particular word that is being used. The decoder provides exactly that behavior. Decoders are also used when we want to identify which button from a large array of buttons has been pressed. A computer keyboard is a good example of something like this. There are over 100 keys on a keyboard, and when somebody is doing some typing, we need some way of identifying which one has been pressed. We can do this using a technique called polling. We set up a counter that simply generates binary numbers in an ascending sequence from 0 up to as many keys as there are on the keyboard. You can do this really fast, so that the entire keyboard can be scanned many times in the time that it takes us to type 2 characters. So the output from the counter is taken to a decoder, which generates a true signal on a wire that corresponds to the binary number and activates a circuit associated with a particular key, so that it's possible to check whether that key has been pressed since the last scan. The next standard building block we'll look at is called the multiplexor. A multiplexor is useful in situations where we have a number of data signals and we want to select one of them to send off to some destination where it will be handled by some other circuit. The circuit symbol for a multiplexor is a triangle that's usually drawn on its side, with many data inputs coming in on the vertical side. Some control inputs that specify which of the data inputs the device will output, connected to one of the other sides, and an output enable control input that turns the whole thing on or off, and a single data output coming from the vertex. If that output enable signal is low, the data output will be identical to the input specified by the control inputs. If it's high, the data output will be 0. In this example there are 4 data inputs, so the control inputs come in on 2 wires, since a 2-bit binary number can be used to identify one of 4 alternative inputs. We can see that there are 7 bits of input in total, so the truth table would have 128 rows if it were drawn out in full. Clearly, we want to avoid having to draw a truth table as big as that, so we take advantage of the regularity of this device to abbreviate the truth table and reduce the number of rows. What we'll do is to show the 3 control inputs on the left-hand side of the table. The output is labelled Q for reasons that we'll come to in a moment, and there are thus 8 input combinations shown in the table. The reason we can do this reduction is that only one output can be high for any of those input combinations. So we can put the data inputs in the output column. Well, how does that make sense? Well, the first row will have input I0 as its output. What we're saying here is that if the input combination where output enable is low and C1 and C0 are both low occurs, then the output depends on I0. If it's high, then the output will be a high. If it's low, then the output will be a low. This can be quite a useful technique for reducing the size of a truth table when there are lots of inputs. It works particularly well when there are two classes of input. Control inputs, in which every possible input combination potentially has a different output, and data inputs that only influence the output under very specific circumstances. Mind you, you could generalize the technique. It would be quite feasible to put complex Boolean expressions in the output column and say, if the input combination on the left occurs, then if the Boolean expression on the right is true, then the output is true, otherwise the output is false. But, well, at least for the moment, we certainly won't be bothering to do that. Well, now we can fill in the rest of the truth table. You'll see that in 4 rows there's an input listed in the output column. So when output enable is low, if the value of the select control input is 0, the output is equal to I0, whereas if the select control input is 2, for example, the output is equal to I2. 0 if it's 0 and 1 if it's 1. Now we can write down the Boolean expression for the output. There are 4 locations in the truth table where the output could be true, so there are 4 terms in the Boolean expression. Each term involves the 3 inputs that are shown formally as inputs on the left-hand side of the truth table, but also that single term in the output column. Then, as usual, we construct the circuit diagram. You'll notice that just as we've broken the usual conventions for drawing up truth tables, so we've broken the usual convention for drawing circuit diagrams, in that not all the inputs and their inverses are listed down the left-hand side of the diagram. The 3 control inputs are shown conventionally, but the inverses of the data inputs are never used, and each of them only contributes to 1 term in the Boolean expression, so we've input them from the left, directly into their own individual AND gates. And of course, we finally need to add an OR gate to OR the results of all the terms in the Boolean expression together and produce the output Q. Remember that I said that I'd explain about the output being labelled Q. Digital circuits are usually constructed as integrated circuits, which are built out of transistors. In circuit diagrams, resistors are identified by the letter R and an ID number, capacitors are identified by the letter C and a number, and transistors are identified by the letter Q and a number. T was already in use for something else, transformers in fact, when transistors were invented. Anyway, the output of a circuit is often identified by the component that produces it. So an output wire labelled Q23 would be carrying the signal output by transistor 23. So, since digital circuits are based on transistors, it was conventional to identify their output signal as Q something, and digital engineers simply carried the idea of using Q on into truth tables. So anyway, that's the circuit for a 4-to-1 multiplexer. We could generalize the whole thing to a larger device with, say, 5 control inputs across the top, specifying which one of 32 data inputs down the left-hand side to choose for output, and the design process would follow the same steps. It would just be a bit more tedious. Our most recent example of building blocks that are used inside computers was the multiplexor, a device that we can use to choose one out of a number of data signals to put onto a single output line. There's a complementary device called a demultiplexor that can be used to take digital data that's presented on a single line and deliver it to one of a number of output wires. And just as the circuit symbol for a multiplexor has a triangular shape that reflects its many-to-one functionality, So the demultiplexor has a triangular shape that reflects a one-to-many behavior. There's a single bit data input shown here on the left, a couple of control inputs. We're using 2 because we're designing a 1-to-4 demultiplexor. Incidentally, the words multiplexor and demultiplexor are often abbreviated to MUX and DEMUX. And finally, 4 single-bit data outputs. So the overall functionality of this device is that the binary number encoded onto the control input at the bottom can be 0, 1 or 2 or 3, and whatever single-bit value is on the data input will be sent to the correspondingly numbered output. If the control number is 1, then the data value will go to output 1. If it's 3, then the data value will go to output 3, and so on. But there's a complicating factor with this circuit, which you will already have noticed. The output wires start with little circles, which indicate that the circuit is inverting. That is, the chosen value will appear at the output, but its voltage will be inverted. If it was a low voltage, in other words 0 volts, at the input to the device, it will be a high voltage, usually 5 volts at the output, and vice versa. This inversion behavior is common to most demultiplexers. So now we write out the truth table. There are 3 single-bit inputs, so there are 8 rows in the table. If the select input is 0, that is, if C1 and C0 are both 0, then we put the inverse of the input on output Q0. There are 2 places in the table where this occurs, in the first row and in the 5th row. If the select input is 1, then we put the inverse of the input on output Q1. That's in rows 2 and 6, and so on. Don't be misled by all the zeros in the output columns in the bottom half of the table. They're genuine data values, they just mirror the input data value. Now, at this stage we'll step back from the current design for a moment to make a very general point. And that is that there's no electrical difference between the voltages used to represent the data values and the voltages used to represent control signals. So as far as the digital circuit is concerned, data signals are electrically indistinguishable from control signals. And at some point, someone particularly clever has sat down and looked at this truth table and another truth table that we've seen previously, the truth table for a decoder, and recognized that from an electrical perspective, they're identical. Oh, sure, the input labels are different, and in the case of the truth table for the decoder on the right, we've written down the OE control signal using voltages instead of binary values, but the electrical representation of the entries in the tables is exactly identical. The only difference is that where the decoder truth table on the right has a control input, the demultiplexor truth table on the left has a data input, and vice versa. But since control and data signals are electrically indistinguishable, this distinction can only be an external convention. If we took the decoder that we've already designed and put data into its control input and 2-bit control signal into its data inputs, then it would function as a demultiplexor. And if you pop down to the local electronics supplier and buy some decoder chips, you'll find that they're labelled as decoder/demultiplexers, and they perform both functions equally well according to how you attach the data and control inputs. And incidentally, that's the reason why the demultiplexor is an inverting device. The decoder has an active low output enable signal, which in the demultiplexor is the data input, so the demultiplexor's output is inverted. So that must be the easiest piece of circuit design ever, a device that changes its function according to how you think about its inputs. Would that it were all so easy.